Hello everybody and welcome again to your channel, Thermal Engineering Concept and the Principle. This is Professor Ali Tarad. I will present some of the important parts of the heat generation in a solid geometry and its industrial application. In this part, we will talk about the heat generation physics cylindrical object. And such application has many industrial use and is important, especially in the applications where there is a need to heat up, such as air heaters or maybe just heating liquid, such as electrical boilers in domestic places for heating water. And I will talk about some of the boundary conditions which are applied to such surface. Thank you for your support, and let us go to the objectives of this video. The main objectives of the present video are related to the heat generation in a cylindrical coordinates, and we will use the one-dimensional heat conduction with heat generation in the solid geometry, some applications in the real engineering, and all of that will be considered in a steady state conditions. Then we will go to a boundary condition, which is a usual one and familiar for such applications, where the surface of the heating element is considered as a constant value. Some exercises for the application of the one-dimensional heat conduction with heat generation in steady state conditions. And finally, as usual, we will approach the closure for the present episode. The heat conduction equation in cylindrical coordinates, if we have a look at this schematic diagram in 3 dimensions, x, y, z, which represents just a piece of a cylindrical object in the coordinate r, z, phi, and that will give us just a sort of schematic diagram where we can apply the heat transfer by conduction in this piece of, for example, solid cylindrical object, and the heat transfer usually is perpendicular to the heating surface. The three-dimensional form of heat transfer by conduction in a cylindrical coordinate is represented by equation number 1, partial square t with respect to r square, plus 1 divided by r partial t with respect to r, plus 1 over r square, and go on until we approach the right-hand side, which represents the rate of change of energy inside that wall. If we consider that the definition for alpha, which represents the thermal diffusivity as K, the thermal conductivity of the material divided by the density of the material times the heat capacity. And usually it is in the units of meter squared divided by second. So for one-dimensional form in steady state, and that means we will take it in the direction of r, radial form, d square t by dr square plus 1 over r dt by dr plus q dot divided by k equal to 0. And the right hand side is equated to 0 because there is no change in for the temperature of the cylinder with time. This equation can be represented in a form that multiply all these terms by r. Then we have the mathematical expression that d by dr of r dt by dr plus rq dot divided by k equal to 0, and that will give a produce for the first integration as rd t by dr equal to minus q dot r squared divided by 2k plus c1, which is represented by equation 4. And if we proceed for the second integration, then we will get t of r equal to minus q dot r squared divided by 4k plus c1, a natural logarithm of r, plus c2, which is represented by equation number 5. And this equation, I will call it the magic equation for the cylindrical surface. Some of the practical applications in industry and in our life in engineering, that is where heaters are used in washing machine, where it is used to heat up water for a certain temperature as the setup of the process in that washing machine. And then we have in the boilers where we produce hot water, such as the boilers are used in domestic places. Also, we have in the kitchen where we can find this in the sort of heater is used for the purpose of cooking of our food. And then we have another application which is for the industrial application, and these forms may be used in industry in a variety of applications, such as air heaters, where we use for heating purposes. Let us consider the case where the heating surface of a cylindrical heater is considered as a constant surface temperature. For example, we have an industrial heating element with a diameter of d and length of L with heat generation inside that element where heat conduction occurs, and the Q is perpendicular to the heating surface. And we need to find an expression for the temperature distribution in the R direction of the heating element where fixed temperature is considered at the wall. For such a case, we will go to the general form d square t by dr square plus 1 over r dt by dr plus q dot divided by k equal to 0, which is the general form for one-dimensional heat transfer in the radial direction under steady state conditions. And equation 5, which is called the magic equation, we need two boundary conditions to find the constants of the integration, C1 and C2. We have dt by dr for this expression is represented by equation number 4, and we have also two boundary conditions to solve this equation. The first one at r equal to 0, dt by dr equal to 0, because the function should be continuous at r equal to 0. And then we have at R equal to capital R. Capital R refers to the outer radius of the element or the cylindrical object. We have T equal to T sub W. If we apply boundary condition number 1, then that will give us C1 equal to 0. Then boundary condition 2 can be used. Then if we apply it to equation number 5, then we will get C2 equal to T sub W plus Q dot R squared divided by 4K. Of course, these values of C1 and C2 can be substituted in equation number 5. Then we will get T of R equal to T sub W plus Q dot divided by 4K times R capital square minus R square, which is represented by equation number 6. If we take the verification for this equation, we have at R equal to 0, if we substitute the value of R equal to 0, then equation 6 will give the maximum of the value for the temperature. And if we apply or substitute at R equal to capital R at the outer surface of the heating element, then we will get T of R equal to TW. Of course, this is represented by equation number 7, where we can see that dT by dr, which represents the temperature gradient of the in the heating element. Let us now consider one of these examples with the numerical values that we have an application, industrial application, where we have a diameter of the heating element is 10 millimeters with a length of 3 meter with a power of 3000 watts, and the heater surface is kept at 120 degrees Celsius. Find the maximum temperature of the heating element, and that means we may use the previous derivative to find the maximum temperature, and as shown in this diagram, that the heat is following the direction of the red arrow, which is perpendicular to the heating element. The general form of Q dot, which represents the heat generation per unit volume, that is power divided by the volume of the heating element. And that could be substituted to get 12.732 times 10 to power 6 watt per cubic meter, where we have the diameter is 10 millimeters, the length is 3 meter, and then we will get the final value of Q dot, which represents the heat generation per unit volume. First, of course, we have to know the position of the maximum temperature. If we use equation 6, dT by dr equal to 0, and that means you have to equate the temperature gradient to 0, then you will get that R equal to 0, and that means the maximum temperature occurs at the center of the heating element. Then, if we take R equal to 0 in equation number 6, and that means you have T naught equal to T sub W plus Q dot capital R squared divided by 4K. If we substitute these values for Q dot and the radius of the heating element and the thermal conductivity, then we will get 125 degrees Celsius, which is the final answer for this example. Here we are, we have arrived at the final part of the episode. that is heat conduction. We have passed through the heat conduction in cylindrical coordinates. We have derived an expression for the temperature distribution. And then we had a worked out exercise from the industrial application. Uh, of course, such um, information can be also found in some references which are gathered in a link in a PDF form in the description box. And thank you for watching. And I hope that I will see you in the second part of this application of heat conduction, one-dimensional steady state conditions in cylindrical coordinate. Bye bye.